Okay, now we can start.
Great, thank you. So let's start this lecture. Let me first correct a wrong statement which I made at the previous lecture when I defined the vanishing order of a function along a prime divisor. I said that one can factorize this function by taking out the local equation of the divisor to some power, I mean this factorization, in such a way that, that the remaining factor, this g, is defined in a neighborhood of the given point x, and I said that g does not vanish on x. So such kind of factorization doesn't hold, of course. It is not true. What is true is that we can factorize in such a way that this g doesn't vanish identically along the divisor. So it may vanish at the point x, but it doesn't vanish identically along d in the neighborhood where g is defined. But after this correction, all
so we cannot make g non-vanishing at x, right?
Yes. G may vanish at the point x, but the point is that g does not vanish along this divisor identically. And after this correction, everything goes well. So all other arguments do not need any change. So everything goes well after that. This is what I wanted to correct. And actually, this correction, which you already see here on the whiteboard, is in the PDF notes, which is on the net disk in the storage. So in the PDF notes, everything is written correctly, like here. Okay, so this was a correction for the previous lecture, and now let me turn to this lecture. I will. I said that I have to say something more to conclude our discussion of divisors and line bundles, and I concluded by the following remarks. So recall that we were considering at the end of the previous lecture, we were considering a line bundle on a normal variety X, a line bundle which is determined by a Cartier divisor delta, and we have considered a finite dimensional subspace in the space of global sections. Finite dimensional subspace M in the space of global sections of this line bundle L. And this gives rise to a rational map. This gives rise to a rational map phi from X to the projectivization of the dual space. This map sends the point small x to the hyperplane in this dual space. To the hyperplane in the space M, which I denoted as M of x. It is the hyperplane consisting of all sections from this finite dimensional subspace M, which vanish at the point x. And this hyperplane can be considered as a point in the dual projective space, P of M star. So this gives you this map, but this map is only rational. It is not everywhere defined, because typically, for typical points X, there exists a section which does not vanish at this point. The set of points with this property is open in X, but outside this set, this subspace M of X coincides with the whole M, and this map is not well defined. So this is only a rational map. And now the first claim which I want to make, is that if the line bundle L is globally generated, which means precisely that for any point small x in big X, there exists a section, a global section of this line bundle which does not vanish at this point. Okay? So if this holds, then there exists a finite dimensional subspace in the space of global sections, which may itself be infinite dimensional, such that the map phi is everywhere defined. The map phi is a morphism from X to the projectivization of M star.
This M can be infinite dimensional, right?
No, M is finite dimensional. The whole space, this guy can be infinite dimensional. If X is not complete, for instance, non-projective, then this guy can be infinite dimensional. But M is always chosen to be finite dimensional. Maybe I was assuming it by the same notation, but let me write it explicitly here that M should be finite dimensional, such that this phi is a morphism. Why so? Because for any point X, you can choose a section which does not vanish at this point. And the set of all points where this section doesn't vanish is an open subset in X. And by the Noetherian property of the Zariski topology, you can choose a finite subcover of these open subsets. So you can choose finitely many sections such that for any point, there is a section from this finite collection which does not vanish at this point. And now I can take for M the linear span of this finite set of global sections. So this is the argument why this claim is true.
Why can we choose a finite number of sections?
Because for any section S, the set of all, so the non-vanishing locus of a given section S is an open subset. And these open subsets cover the whole variety, because L is supposed to be globally generated. Yes. And if you are given an open cover of an algebraic variety, you can always choose a finite subcover.
Well, this is a fundamental theorem in algebraic geometry, right?
Yes, this is a property that Zariski topology is Noetherian. Noetherian implies this statement.
Noetherian, yes.
Yes.
I understand. Yes.
So it stems from the Noetherian property of the Zariski topology. Okay. Well, let me also state the second claim. So we have constructed a morphism to a projective space from a globally generated line bundle and a finite dimensional subspace of sections of this line bundle. And the second claim says that actually any morphism to a projective space comes from this construction. Any morphism phi from X to some projective space P to the n comes from some line bundle L. In this case, L is just the pullback along phi of the line bundle O of 1, whose fibers are linear forms on one-dimensional subspaces in the n+1 dimensional overlying vector space of Pn. And this space of sections in the above notation, which defines this map phi, is nothing but, in this situation, it is nothing but the pullback of the space of sections of this O1 on Pn. This space of sections is just the space of linear forms in projective coordinates on Pn. All linear forms in projective coordinates. These are the sections of this line bundle O of 1. Okay? So basically,
so
yes.
do we require the morphism phi to be everywhere defined?
Yeah. When I draw this full arrow, not dashed arrow, this means that it is everywhere defined. Dashed arrow means a rational map. It is not everywhere defined. This is standard notation in algebraic geometry. So this guy indicates a rational map, and this kind of arrow indicates a morphism, an everywhere defined map. Okay. Yet another piece of terminology which you probably know, at least you should know if you studied algebraic geometry. So the Cartier divisor delta is said to be very ample. Very ample. If the map phi defined by some finite dimensional subspace of global sections of the line bundle associated with this Cartier divisor, if this map phi is an embedding of X in a projective space. So if this map phi is an embedding, this means that this subspace M can be chosen in such a way, this subspace M can be chosen in such a way that this map is an embedding. Then we say that the divisor delta is very ample. And a weaker property, the divisor delta is said to be ample if some multiple of it is very ample. Some positive multiple of it is very ample. If there exists a natural number n such that m times delta is very ample.
Well, I want to ask a question.
Yes, please.
Different subspace of the global section induce different morphisms. So we call the divisor delta very ample if any one of the we only need one of the morphism to be embedding, right?
Yeah. If there exists such an M. So if phi is an embedding for some, let me write it here, for some M in the space of global sections of L. Okay. When you let me comment about the definition of an ample divisor. For an ample divisor, such an M may not exist. But if you replace delta with a multiple, then such an M exists. replacing delta with a multiple means that you replace the line bundle L with its mth tensor power. So maybe not the line bundle itself determines an embedding of X in a projective space, but some its tensor power determines an embedding into the projective space. This is the definition of an ample divisor. Okay, so this is, I hope, all that I need for the moment from the theory of divisors and line bundles on algebraic varieties. And now let me come back to the proof of Sumihiro's theorem. If there are no questions for this first slide, then maybe let me turn to the next page and come back to the proof of Sumihiro's theorem. So what is our situation? We have, let me recall what is Sumihiro's theorem. We have an action of a connected algebraic group, not necessarily reductive, on a normal algebraic variety. And we want to find a G-stable quasi-projective open neighborhood well, quasi-projective open neighborhood U of a given point in X, of a given point X small in X. So for any point X small, we want to find such a quasi-projective open G-stable neighborhood. So what we have done so far, we have taken an affine neighborhood, U prime, open affine subvariety in X, containing the given point X small. But we do not assume, of course, that it is G-stable. And we have proved, this was our first lemma, we have proved that the complement of this U prime, of this affine open subset, which we denoted by D, is a union of finitely many prime divisors. D1 ds, so these D1 ds are prime divisors. Okay. So now the second lemma, which I need for the proof, says that each of these prime divisors, each of these DIs, is Cartier. Maybe not on the whole X, but on X, on the complement of the closed subset, which is the intersection of all G shifts of DI over all G in big G. So what we do, we move the divisor DI, the prime divisor DI, by all elements of the acting group. And we remove the intersection of these shifted divisors from X. What remains, what is left, is a G-stable, again, a G-stable open subset. And I claim that my divisor di is Cartier on this open subset. So the intersection of di with this open subset is Cartier. Okay, this is the statement. Now, how to prove it? Proof. So without loss of generality, we may assume that this intersection is just empty. Otherwise, we can just remove this intersection from X and replace X with this open G-stable subset. So we may assume that X itself is this open G-stable subset. Okay. Now we know that any divisor is Cartier on the smooth locus. So in particular, di is Cartier on the smooth locus of X. And since it is Cartier, it gives rise to a line bundle. Let me denote it like this, L over reg. A line bundle over the smooth locus.
Well, Professor, I have a question.
Yes, please.
Well, the condition for the Spherical theorem requires X to be just require X to be normal, right?
Yes, yes. The condition is here. So X is normal and G is connected.
We don't require X to be connected, right?
Well, by definition, I assume normal to be reducible.
Oh, yes. I forgot about that. Sorry.
But actually, since since this statement is local, you may state it even for disconnected normal varieties, because the statement is local. We are speaking about neighborhoods, so we may assume X be connected.
Well, I'm not doing that. I mean, the open subset of a normal variety is still normal, right?
Yes, sure. Normality is a local property. Sure. More questions?
Professor, can you say again why we can assume this condition that GDI?
Yeah, just because otherwise, let me write it here. Otherwise, you may just replace X with this complement, with X minus this intersection. Okay? You make your X smaller, but actually it is still a G-stable normal variety, so all assumptions are preserved. Just remove this intersection, and then you get that on the remaining part, the intersection will be empty. Okay? Maybe I remove this, what I just have written, because...
Yes, so would DI be cut off something here?
Say it again?
If we cut off this intersection, may we have a smaller DI? I mean, DI.
Yeah, of course. You intersect your divisor with the open subset. You get a divisor on this open subset. So I still denote it by DI because it is dense in what was before. It is just an open subset in DI. But of course, DI is changing because now you come to an open subset and you get a divisor on this open subset. Okay.
actually does not affect the condition that we.
Yes.
Okay.
Yes, of course. So let me go back to the proof. Since my di is Cartier on the regular locus, on the smooth locus of x, this means that the intersection of di with this smooth locus is a Cartier divisor on the smooth locus. We can associate a line bundle to this Cartier divisor, which is in our notation, it is written like this: O sub x reg of di intersect with x reg. So what is written in brackets is a Cartier divisor on the regular locus of x. Okay, and also we have a canonical section corresponding to this divisor. The section, let me denote it just by small s, a section of this line bundle whose divisor is exactly this guy. So the divisor of S equals di intersect with the regular locus. Okay, then recall that we can lift an action of the action of G from the base to the total space of the line bundle. In particular, in this case, the group G acts on X regular, and we can lift this action to the action on this line bundle, maybe after replacing G with a finite cover. So I was denoting it by G prime. So we can define an action of some G prime, which is a finite cover of G, on this line bundle, which is compatible to the projection onto the base. And therefore, we may act on sections. And if you take a section, S and act on it by some element G small, then you get another section whose divisor is obtained from the divisor of the section S by acting of this by the action of this element G. So its this divisor will be G di intersect with X reg. In particular,
can we ensure
yes.
the existence of S?
Say it again.
How can we ensure there exists a global section S?
Well, because this divisor is effective. This is the prime divisor. It is an effective divisor. So a section S with this divisor has no poles.
And another question. So a prime divisor is always Cartier on the regular point of X, right?
Sure. Any divisor is Cartier or on regular points.
Oh, any divisor, yes.
Any divisor. Any divisor is a linear combination of prime divisors. And since prime divisors are Cartier, any other divisor is also Cartier. This I mentioned on my previous lecture. So we have these shifted sections, and their divisors are shifted by the action of G. In particular, since this section has this divisor, it is nowhere vanishing on the complement of this divisor. And therefore, our line bundle, L regular, is trivial on the complement of this divisor. So on X smooth, X regular minus G di. Because this section GS nowhere vanishes on this open subset. And if you have a non-vanishing section, nowhere vanishing section, then this trivializes your line bundle. Let me denote this open subset U sub J regular. And this holds for any G. For any G, well, I mean this triviality of this line bundle holds for any G on the respective open subset. Okay? So we have a trivialization, a trivializing cover of the line bundle L reg.
Sorry.
Yes?
Yeah. So this G is in the G prime or the original G?
Say it again, please.
So this small G here is in the group G prime or original
Yeah,
G?
sure, yeah. Small g is in G prime. Yes. Well,
the
in
G
fact,
prime, it depends on the choice of your DI. Because it depends on.
Yeah, I mean, for any G, you have this open subset, and this line bundle trivializes on this open subset by the choice of this non-vanishing section.
He means that the group G prime is determined by the line bundle L.
No. This group G prime comes from a theorem in the previous lecture. This group G prime is one and the same for all line bundles.
It's independent of line bundle, yes.
It is independent. It is independent. The notation is the same as on the previous lecture. This group G prime can be chosen independently. By the way, you can replace this line bundle by its tensor power. This means that you replace DI by its multiple, by its positive multiple, and then you may obtain that even the group G will act on your line bundle. But I don't need this. I just don't need this. For me, G prime is okay. The action of G prime is okay. So let me continue the proof of the lemma. So we have a trivialization of this line bundle on each of these open subsets. Trivialization given by the choice of these local sections, which by these sections, global sections, which do not vanish on the respective open subset, nowhere vanish. But if we have two such trivializations on two open subsets, say if we restrict the line bundle L reg to, say, to U sub G reg. And also we can restrict the same line bundle L to another open subset, say to U sub H reg. G and H are two elements of the acting group. Then we have a trivialization here. This is isomorphic to the direct product of the base and the one-dimensional vector space. And we have a trivialization here of the same type. But we can restrict ourselves to the intersection of these two open subsets. So here we have an open subset. We replace the base by the intersection. UG reg intersect UH reg cross K to the 1. And here as well, you have a similar open subset. But these two trivializations of my line bundle on the intersection of these two domains are different. So we have a transition map. We have a transition map from here to here, given by some invertible functions. Let me denote it like f sub jh. These are invertible functions on the intersection of these two domains. I hope I have space here to write. Maybe not. Let me try. The intersection of these two domains. So these functions are invertible. Okay. These are what are called transition functions from one trivialization to another one. Transition functions. So basically, you change the identification of the fiber over a point in this intersection with the one-dimensional vector space, with the fixed one-dimensional vector space. And changing this identification is given by a scalar multiple. So at each point of this intersection, we have a scalar multiple, and this gives you this transition function. Okay, so this is the line bundle L-reg, corresponding, let me come back to the previous page, corresponding to the Cartier divisor di on the regular locus of X. The line bundle and its trivialization. But now let me consider the whole X. And let me decompose it as a union. So let me write that X, my X, can be decomposed as a union over all elements G of open subset U sub G, where U sub G is defined in the same way as U sub G reg, but now you take the whole X and remove the shifted divisor di. So for this previous open subset U sub G regular, you have taken the regular locus, the smooth locus of X, and removed this divisor. And now you take the whole X. Then by the normality property, so by the normality property, we can say that these transition functions F sub JH, these transition functions are defined and nowhere vanishing, invertible on the intersection of these two open subsets in the regular locus, in the smooth locus. But now, since the variety X is normal, the complement of the smooth locus has codimension at least 2. And this means, by normality, that this function Faj extends over the intersection of Uj with UH. So not only on the smooth locus of this guy, but on the whole intersection, because the complement is of codimension at least 2, and small singularities are removable. Small singularities of a rational function are removable. And since this function Fjh was invertible, had neither zeros nor poles on the smooth locus of this intersection, then this function is also invertible. So this function f sub jh is an invertible function on this open subset UG intersect with UH. Okay. This means that this set of functions f sub gh can be considered as the set of transition functions for a line bundle over the whole X. So you may consider trivial line bundles on these open subsets U sub j over all j, U sub g over all g, and you glue together these trivial line bundles on these open covering subsets by means of these transition functions. So these transition functions allow us to glue trivial bundles over this cover. So this means that the line bundle which we had before, this L reg, extends to the line bundle over the whole X. and also the section S small of this line bundle extends to the global section of this line bundle L. So extends over X. And the divisors essentially do not change, because when we pass from the regular locus to the whole X, we add something of codimension at least 2. So the divisor of this section S will be the same. And this, yeah, so we have that on X, the divisor of this section S will be just di. And this proves the lemma. We wanted to prove that di is Cartier. We constructed a line bundle and a section such that the divisor di is just the divisor of this section. This means that it is Cartier. Okay, so we have proved this lemma. Any questions so far? No questions? Okay. Then let me finish the proof of Sumihiro's theorem.
Okay, so
yes. Okay.
Does this lemma mean that on this X every divisor is Cartier?
This lemma means that di is Cartier under our assumption, which we make here. We assume that the intersection of its shifts by the group action is empty.
Ah, okay.
If it is not empty, then it is Cartier only on the complement of this intersection. And this is the statement of the lemma. Okay?
Okay, thanks.
Great. So let me finish the proof. Let me now finish the proof of Sumihiro's theorem. So consider, let me come back to this notation. So we have an affine open neighborhood of my point X small. And the complement of this affine open subset is a union of finitely many prime divisors. Let us take their formal sum. So let me denote by delta just the formal sum of these prime divisors. And the previous lemma implies that this delta is Cartier outside the intersection of all shifts of the union of this prime divisor. So it's Cartier on the open subset U, which is X minus the intersection of all shifts of this D over all G. So D is just the union of these DIs. And we remove the intersection of D with all its shifts by the action of the group. In other words, this U is nothing but the G span of U prime. Because U prime is the complement of D. When you shift D, then you shift U prime. So GU prime is the complement of the shifted D. And when you intersect all these divisors and remove this intersection, this means that you take a union of all shifts of U prime by the action of G. Okay? So this is again an open subset. Maybe I should write here. I'm sorry. I made a typo. Let me write here that it is Cartier. It is Cartier on this U. Okay. So now let me consider. So let's remember this observation. Let's keep in mind this observation, and let me continue the coordinate algebra. Let me consider the coordinate algebra of my affine open subset U. It is a finitely generated algebra. It is generated by finitely many regular functions on U prime, say f1, fm, f1, fn. And each of these functions is regular on U prime. This means that if you consider this function as a rational function on the whole X, then the poles of this function sit outside U prime. The divisor of poles of each of these fj's is a linear combination of these di's with some coefficients. A sum over I, some coefficients k, I, j, times di. Now let's take the maximal number, the maximum of these kij's. So put m equal to the maximum of these numbers. And let's consider a multiple of delta, the mth multiple of delta, and the canonical section. So let me denote by S naught, the canonical section associated with the divisor m delta. This is a section of the respective line bundle over this open set U, because delta is Cartier on U, and we have the respective line bundle and the respective canonical section. Okay, so the divisor of this S naught is m delta, and if you multiply this S naught by any of these functions fj, then you get a section of the same line bundle, which also has no poles, because the divisor of poles of fj has coefficients which are smaller or equal than this m. So after multiplication with S naught, the poles of fj are killed. We get a regular section. Okay. Now we have this line bundle associated with the Cartier divisor m delta on this U, and everything is G equivariant, so we can lift the action of G to this line bundle, maybe after replacing G with its finite cover. But if we take M big enough, we can even lift the action of G itself. But let me lift it to the G prime action as before, just not to confuse you. So choose a G prime stable finite dimensional subspace M in the space of global sections of this line bundle over U, which contains all these sections S naught, S1, etc., Sn. So we may take the linear span of these sections. It is a finite dimensional subspace, and then we can span it to a bigger subspace by the action of G prime. Since it is an algebraic group action, then finite dimensionality will be preserved. So we have such a finite dimensional subspace. And
how can we conclude the finite dimensional?
Well, actually, this is a statement. Let me again refer you maybe to this paper of 4 authors Knop, Kraft, Luna, and Lust. For the proof, the claim is that for any section in this space of global sections of a line bundle over normal variety with the action of the group lifted to the line bundle, for any section, for any global section, you can choose a finite dimensional G-stable or G-prime stable subspace containing this section. So the whole space of sections is infinite dimensional, but it is exhausted by finite dimensional G-stable subspaces or G-prime stable subspaces. This is a statement. This is not obvious, but this is a general statement, and I refer you to this paper for the proof. I think I have no time to prove it now.
So the S0, S1 up to Sn here is the same as those above.
S0, S1 are the same as above. Yes, yes. These Sj's which were defined above. So S0 was defined as the canonical section, and the other Sj's were defined by multiplying this canonical section with Fj's.
So it is G prime stable because the set U is G prime stable, right?
Yes, yes. G acts on everything here. So G acts on U, and also this action lifts to this line bundle, as we know. Well,
Okay.
we didn't prove it, but it was stated.
Okay,
Maybe you have to replace G with G prime for this purpose. To lift to the line bundle, maybe you have to replace G with G prime, but it doesn't matter essentially. And now I use the property that any of these sections can be included in a finite dimensional G stable subspace or G prime stable subspace. And after that, I take just the sum of these finite dimensional subspaces. And this will be my M. Okay? So finally, what we get, this finite dimensional subspace of global sections gives rise to a morphism.
So this G prime is associated to the normal variety U, right? Not the whole X.
Yes, yes, yes. It is associated to U, right? But actually, this G prime can be well, okay, yeah. Let me be careful here. It is associated with U. So this defines you. This defines you a map phi from U to the respective projective space. A map phi from U to the respective projective space P of M star. And I claim that this map is an embedding, that it is everywhere defined and it is an embedding. Let me explain why. Because if you take a smaller open subset, say U prime, excuse me, if you take U prime, then this U prime is as an open subset in U defined by non-vanishing of S naught, because the divisor of S naught is the complement of U prime in U. Yeah, this divisor is delta. It is a complement of U prime. Yeah, so on this U prime, the section S naught nowhere vanishes. And this means that U prime is mapped to an affine chart of this projective space defined by non-vanishing of the section S naught, now viewed as the coordinate function on M star. This map is an embedding, even closed embedding, because it is a map between two affine varieties, And the inverse map of coordinate algebras is surjective. So the coordinate algebra of this affine chart, it is just spanned by ratios as j over s naught. And these ratios map to these functions f, fj, as we see from this formula. The functions fj generate the coordinate algebra of u prime. So this means that the inverse map of coordinate algebras is surjective. And for the affine varieties, this means that this map is a closed embedding. And since everything is equivariant, we may act by an element g here, and here. And this will be still a closed embedding. But these guys, gu prime, are the open cover of u. So if you have a map which is a closed embedding locally on an open cover here and here, then it is an embedding, maybe not closed embedding, because this chart may not cover the whole P of M star, but it is an embedding here. So we have proved that the divisor delta, or better to say its multiple, mth multiple, gives rise to an embedding of my U into a projective space. And this means that U is quasi-projective. So hence, U is quasi-projective. It is embedded in a projective space. Quasi-projective, G stable open neighborhood of X, the one which we have looked for. This ends the proof of Sumihiro's theorem. So the proof is complete. And also, at this point, I stopped the first half of my lecture, and even seven minutes later than the break time. I'm sorry for that, for taking 7 minutes of your break. I will shift the break, the 10 minutes break, by this 7 minutes. But let me stop the first half now. If you have any questions, then please go ahead.
So any subvariety of projective space is quasi-projective, right?
By definition, yeah. This is just by
definition. A quasi-projective variety is the open set of projective subvariety.
Yes, open in projective. But what is a subvariety? A subvariety is just the thing like this. You take a closed subvariety and you take an open subset in it. This is what you get is what is called a subvariety. So each subvariety is by definition locally closed. Mm-hmm.
So how can I prove that U is open in its closure in the projective space?
Well, because locally, let's take a look here. Because locally on these charts it is just closed. Okay. So if you restrict this embedding to an affine chart given by non-vanishing of this linear function on M star, then you get just this embedding, and this embedding is closed. Because as I explained, these two guys are affine varieties, and the inverse map of coordinate algebras is surjective.
Yes, it's closed. So the openness of U in its closure is derived from this?
Yes, exactly. Exactly. Because locally it is just a closed embedding. Then globally it is a locally closed embedding, which means that the image is open in its closure. More questions?
Yes, Professor.
Yes, please.
So locally closed embedding means it's open in its closure?
Yes. So this means that U is mapped isomorphically onto an open subset in some closed subvariety here. U is isomorphic to its image, and its image is open in its closure. This is exactly what you have said. Mm-hmm. More questions?
It is a standard algebraic geometry result, right?
Yes, yes, of course,
Okay.
of course.
Okay.
So if you have no more questions so far, then I guess we have yet some 4 minutes for the break. Let me turn off my microphone, but I'm here, and if you want to ask anything, then just ask, and I will switch on. Well, I think it's time to come to the second half of my lecture. So we have proved the Sumihiro theorem. Let me accompany it with a concluding remark. So remark, if X itself were quasi-projective, so in the notation of the Sumihiro theorem, if X itself were quasi-projective, then we may choose an ample divisor on it. since it is quasi-projective, it is embedded in the projective space, and there exists an ample and even very ample divisor on it. We may choose a multiple of this delta, which is very ample.
Well, is the probe the if X is positive projective, the divisor corresponds to the hyperplane section is ample.
It is even very ample. If you consider the projective embedding of X and take the divisor corresponding to the hyperplane section, it is even very ample. But in particular, it is ample. So very ample is a stronger condition than ampleness.
Oh, so why don't we choose a very ample?
Well, you may choose. Yeah. I mean, just this is how I formulated this. You may choose delta be very ample at the very beginning, if you like. No problem. Yeah. So, but what is an advantage to replacing delta by a multiple is that the respective line bundle O of m delta, which is O of delta to the tensor power m, we can choose m big enough to get this line bundle to be G linearizable. This means that you can lift the action of G itself, not of G prime, but of G itself to this line bundle. G linearizable. Even if delta were very ample at the very beginning, the action of the group G on X might not lift to the line bundle defined by delta. But if you replace delta with its tensor power, which is still ample and even very ample, then we can get such a lifting for the G action itself. Okay, and arguing as before, we see that there exists a G-stable finite dimensional linear subspace.
Hey, so
in the
Professor,
space
I
of
have several questions. So
yeah.
I mean, if data is ample, so there exists some positive number m such that the m multiple of delta is very ample, right?
Right.
So that is it true that for every number bigger than m, the multiple of delta is very ample?
Well, for any number divisible by m, this is true.
Divisible by m.
Divisible by m.
So the G linearizable or the multiple we choose such that the G linearizable is exists is the least common multiplier of the very ample index and the
yes, something like this, exactly. Yeah. Okay, so we can choose, arguing as above, as before, we can choose a G-stable finite dimensional subspace of global sections such that the respective map from X to the projectivization of its dual, such that the respective map from X to the projectivization of the dual space is an embedding, a G equivariant embedding. So roughly speaking, you can say that a connected algebraic group action on a normal quasi-projective variety always comes from a linear representation in an overlying vector space corresponding to the projective space in which your variety is embedded. In a sense, every connected algebraic group action on a quasi-projective normal variety comes from a linear action. So normality is essential here for this statement to be true. Normality is essential. So I didn't write it here, but let me again write it here, that I assume that x is normal, of course. Normality is essential, as the following example shows. Let me consider an example. So consider the nodal curve on an affine plane, which is defined by this kind of equation: x cubed plus x squared equals y squared. Let me draw this curve for you on the affine plane. So it looks like this. So let this be maybe here. Let this be the y-axis. Let this be the x-axis. Excuse me. Not this kind. So this is the y-axis and x-axis. No, not like this. We have x here, and we have z. We have y here. And this curve given by this equation looks like this. Let me try to draw it accurately. It's not as easy. Something like this. This is an affine curve, but you can take its projective closure. So you may consider a curve on the projective plane. To give an equation for this projective curve, you have to add another projective coordinate. You have to consider x and y not as affine coordinates, but as projective coordinates in P2. And you have the third projective coordinate, which you have to include in the equation like this. So let me modify this equation by adding z here and z here. Now it is a homogeneous equation in x, y, z, which are the coordinates on the projective plane, and the curve given by this equation, let me denote it by x, is a nodal projective curve. It has a singular point, this one, which is on the affine part, and the intersection of this curve with the infinity line, with the line at infinity, is just a single point which is smooth. So this picture now shows you the affine chart where z is equal to 1. And the line at infinity is where z is equal to 0. You can easily calculate that at infinity you have a point with coordinates x and z equal to 0 and y equal to 1, say, non-zero. A single point at infinity, and it is a smooth point. So this is a nodal curve, and it looks like this. So you have this singular point, the node, and this curve looks like this on the projective plane. So you have a point at infinity. For this reason, it is sometimes called the 8 curve. 8 curve. The normalization of this 8 curve is just the projective line. So x tilde, the normalization. This is the normalization map, which I denoted previously by nu, is just the projective line. And this normalization map can be visualized as follows. So on the projective line, we have 2 points, 0 and infinity. And the projective line goes like this. And this normalization map just identifies these 2 points, 0 and infinity. So this picture goes to this picture. You identify 2 points on the projective line, and you get a singular projective curve like this. Okay? You can write this map by formulae in projective coordinates, but I don't want to do it now. I can leave it as an exercise for you to write down the formula for the normalization map in projective coordinates, in appropriate projective coordinates. Now, we have an action of the multiplicative group, let G be K star, acting on the projective line in an obvious way. So a point with projective coordinates, say U0 and U1, is mapped by an element T, which is a multiplicative parameter on this group, to the point with the projective coordinates U0 and TU1. So this is a natural action of the one-dimensional torus on a projective line. And this action fixes the points 0 and infinity. So 0 and infinity, these points are given by U0 or U1 equal to 0. So U0 equal to 0 is the infinity point, and U1 equal to 0 is a 0 point. These 2 points are fixed by this action, as it is obvious from this formula. So fixed points. And when you glue together, when you identify these 2 fixed points by means of this normalization map, then this action of G descends to the action of G on X. So this action descends to the action on X. Again, you can write down this action in principle by explicit formulae, but let me skip it. So an exercise for you. Is to prove that there does not exist a linear representation of this multiplicative group G on some vector space such that X can be embedded in the projectivization of this vector space equivariantly. So this embedding commutes with the action of G. So in other words,
Professor, I want to ask a question.
Yes, please.
What kind of knowledge do we need to know to solve this question? Because in fact, I'm not majored in algebraic geometry, and many basic facts is not familiar to me.
Well, of course, you need to know some algebraic geometry, but I would say that if you believe that the action, if you believe that this action on the projective line descends to the action on here, with the singular point being the unique fixed point for this action. So on the projective line we had 2 fixed points, but now they map to one and the same fixed point. Here, this is this one. And if you believe in this fact, then this exercise is not that complicated. So let me give you a hint how to prove it. Maybe let me write it here. I have some some space here. Try to prove that for any linear representation of the multiplicative group G, which is K star, in any vector space, the closure of any orbit in the projectivization of this vector space. So you take a vector in V, you take the respective point in the projective space, and you close up the orbit of this point. So prove that this orbit has two fixed points. If you prove this, then you can easily derive the statement of this exercise. Okay?
Okay, thanks.
Mm-hmm. Well, so this example shows that normality is essential for this remark to be true. Because for normal x, we can always embed it into a projectivization of some linear representation of G. But in the example, this nodal curve is non-normal, because for curves, normality means smoothness. This nodal curve is singular, and it cannot be embedded in the projectivization of a linear representation of G, compatible with the action of G, compatibly with the action of G. So normality is essential. Okay, now let me turn, so this was actually a big digression about divisors, Land bundles, and then we proved Sumihiro's theorem, which is actually more general than the scope, the topic, the subject of my course. Let me now come back to the subject of my course, that is to spherical varieties. What I'm going to prove now what I'm going to do now is to prove some finiteness results for spherical varieties. Finiteness theorems. I will formulate precisely in a minute what do I mean. So I will restore my notation for spherical varieties. Let now G denote a connected reductive algebraic group. Now it is reductive, as before. And X be a spherical G variety. Let me remind you that spherical means that a Borel subgroup of G acts on X with an open orbit. Of course, G itself also acts with an open orbit, but the condition is stronger. A Borel subgroup in G has to act on X with an open orbit. And also let me remind you that I assume that spherical varieties are normal. So I don't write it explicitly, but when I speak about spherical varieties, I assume normality. Actually, it is not essential for the theorem which I'm going to formulate, but it will show up in the proof. So let me just, for safety and for convenience, assume that X is normal, as I always will do. Now, the theorem which I'm going to prove, well, it is the first theorem, but I am not sure that I will have time to come to the second theorem on this lecture. But anyway, let me call it theorem 1. If you are given a spherical G variety, then G always has finitely many orbits on it. So the action of G on a spherical variety always has finitely many orbits.
Hey, Professor, do we prove that spherical variety is normal?
No, this is an assumption. This is an assumption. So I assume normality. But of course, if you have a non-normal spherical variety, you can normalize it. There is a normalization construction, as you remember. And the normalized variety will be still spherical. So you can make any spherical variety normal by a small modification. But let me assume normality from the very beginning. It is not essential for this theorem, because if X were non-normal, then you can normalize it. And if you prove that G has finitely many orbits on the normalization of X, then of course it will have finitely many orbits on X itself, because you have a surjective map, surjective birational finite map from the normalization of X to X itself. But I mean that for other statements, for other theorems, for instance, for classification of spherical varieties, it is convenient to assume that they are normal. So let me put the normality assumption from the very beginning. Okay? So the action of G on any spherical G variety has only finitely many orbits, and each of these orbits is again a spherical homogeneous space.
So X is homogeneous, right?
No, X is not homogeneous. X is not a homogeneous space. X is not a spherical homogeneous space. S is a spherical variety. It contains a spherical homogeneous space as an open subset, as an open orbit. And the statement is that all other orbits, there are finitely many other orbits. The number of orbits on a spherical variety is always finite. Okay? So this theorem goes back to Cervedio, who proved it for the affine case in 1973. And the general case was proved by Luna and Wust in 1983, 10 years later. Okay, now let me prove this theorem. Here we go. Proof. Well, first of all, we can apply the Sumihiro theorem. Since we assume that X is normal, we can apply it directly. We do not need any normalization. So by Sumihiro's theorem, we can cover X by finitely many open quasi-projective G-stable subsets. So these Xi's are G-stable, open, and quasi-projective. This is just by Sumihiro's theorem. It suffices to prove that G has finitely many orbits on each of these Xi's. In other words, we may assume that X itself is quasi-projective.
But how do we derive the finiteness from the Sumihiro theorem?
No, finiteness is again a consequence of the properties of Zariski topology, the Noetherian. Yes. This is by Noetherian property, by the Noether property. So it suffices to prove this theorem for each of these Xi's. So we may assume that X itself is quasi-projective. And since X is quasi-projective, by the remark on the previous page, it can be embedded G equivariantly in the projectivization of a linear representation of G.
So Professor,
Mhm.
we require xi to be pairwise disjoint, right?
No, no, of course not. Of course not. They are not pairwise disjoint because X is irreducible, and any two open subsets intersect. So these xi's overlap very strongly.
So we for every point in X we choose equivariant a G stable open subset by Spherical theorem, and we choose finitely many to cover X, right?
Exactly, exactly. In particular, all these xi's contain the open G orbit in X. So we may assume X itself quasi-projective and even more embedded in the projectivization of a linear representation of G by the previous remark. Now replacing X with its closure in the projective space, replacing X with its closure in the projective space, we may assume that X, so may assume that X is just a projective G-stable subvariety in this projective space P of V. So G-stable projective subvariety. So we reduced the proof to the projective case. Next, we want to reduce to the affine case. This is a standard thing which is called affinization. Let me digress a little bit on it, elaborate on affinization. So what is affinization? Given a projective variety X, you may consider the affine cone over it. Let me denote it as X hat. This is an affine cone, the affine cone over X sitting in the overlying vector space. So affine cone over X.
So the technique we use is that if we prove the finiteness of the orbits on the closure of X, then we prove the finiteness of orbit on X, right?
Yeah, sure. We reduce the proof to some special case. These are just steps of the reduction. So now we want to reduce to the affine case, to the case where X is affine. And to this end, we replace your projective X by the affine cone over X. It is sitting in this vector space V. And also, let me replace the group G, the acting group G.
The affine cone over X. X is projective now.
X is projective, and you take a cone over it, in the usual sense of algebraic geometry. Okay? So let me also replace the acting group G by a bigger group. Let me denote it as G hat, which is the direct product of G cross K star. So G acts as defined because V is a linear representation of G, and K star will act by a scalar multiplication. So K star acts by scalar multiplication on this vector space V. And it preserves this action of G hat, preserves the cone X hat, of course. This group G hat is also reductive, and the Borel subgroup in G hat, let me denote it as B hat, can be chosen to be the product of a Borel subgroup in G, which was B, and this K star. So this guy, B hat, is a Borel subgroup in G hat. Borel subgroup. Okay. Now, an observation, which is almost obvious, just if you think a little bit about it, is that the set of G orbits or B orbits in X is in a one-to-one correspondence with the set of G hat orbits or B hat orbits in X hat. Okay, so we have let me try to draw some kind of a picture for you. So we have this cone. We have this cone X hat. This is the origin. We have a projective variety, which is a projectivization of this cone, this X at the infinity. And the group G acts on X, while the group G hat acts on X hat. And since G hat contains scalar maps, all these lines are contained in G hat orbits on B hat orbits. And this means that if you take any orbit in X, let me choose a different color, like, I mean, like maybe right color to be visible. If you take any orbit in X, so orbit for G or for B, doesn't matter, then the cone over this orbit will be an orbit for G hat or B hat. So the cone will be the orbit over G hat or B hat. So this is an explanation for this bijection. Okay. In particular, this implies that X hat is spherical for the action of the group G hat. Because sphericality means existence of an open B orbit. X was spherical, there exists an open B orbit in X, and the cone over this orbit will be the open B hat orbit in X hat. So X hat is also spherical. And if we prove that the number of G hat orbits in X hat is finite, then thanks to this bijection, we'll prove that the number of G orbits in X is also finite. So replacing X with X hat and G with G hat reduces the proof to the case where X is affine. So we may assume that X is an affine variety, affine spherical variety. And now it remains to prove the theorem in this case. Okay, any questions so far? So this maybe let me say that it was the first part of the proof, which is the reduction to the affine case. And now, before I turn to the second part of the proof, maybe you have any questions on the first part, how to reduce to the affine case. Is it clear? Well, I hope so, at least.
Well,
Mhm.
The X hat here is an open affine variety.
No, X is a closed affine subvariety in the vector space V. because
Close?
yeah, because I mean because x were projective in P of V. Yeah, x is projective. X is closed in P of V, right?
But x hat does not contain the original point. So x.
No, it contains the origin.
Oh,
Yeah, you are right. You are right that I made a wrong statement here. You are right in the sense that there is a bijection. There is a bijection between orbits in X and orbits of these hat groups in X hat without the origin. You have this origin to be removed in order to get this bijection. Okay? So the cone X hat contains the origin, but the bijection for orbits holds for this cone without the origin. So this guy is an open subset in X hat. And X hat itself is closed. But removing a single point doesn't change finiteness. So if the set of orbits were finite with this point, it would be finite without this point, and vice versa. So this is a harmless thing to remove a single point. Okay? Okay. So now let me turn to the second part of the proof, which will be the end of the proof. And to prove that, let me prove that the theorem holds for affine spherical varieties. So let Z be any closed irreducible G-stable subvariety in X. Closed irreducible G-stable subvariety. Okay? I want to prove that Z contains an open B orbit. In other words, open in itself, in Z, not in X, of course. In other words, I can say that Z also is a spherical variety, maybe not normal. I do not prove normality at this moment, but in fact, Z will be also normal, but this is a more complicated thing. The normality of a closed G-stable subvariety, the spherical variety, is yet another theorem, which I won't prove now. But I can say that the statement basically says that Z is a maybe non-normal spherical variety. Okay, so how to prove this? Yes.
The statement is equivalent to Z is spherical, right?
Exactly. But maybe non-normal, because I have to be careful here, because I assumed at some point that all my spherical varieties are normal. So when I say spherical variety, I assume normal spherical variety. But here it is not the case. Here I do not say that Z is normal. In fact, it is normal, but I do not prove it here. Okay? Well, let me prove this claim by contradiction. So assume the contrary. Otherwise, if it is not true, otherwise, let me remember the characterization of spherical homogeneous spaces. So a homogeneous space is spherical if and only if, at least in the quasi-affine case, a homogeneous space is spherical if and only if the representation of the group G in its coordinate algebra is multiplicity free. That is, each irreducible submodule occurs only once. Actually, in the proof, which was, I guess, on my fourth lecture or so, we didn't use homogeneity. So the same statement holds for any G variety. I can say that an affine G variety is spherical if and only if the representation of G in the coordinate algebra of this variety Z is multiplicity free. the proof is exactly the same. Nothing changes. So if we assume that Z, if we assume the contrary, if we assume that Z does not contain an open B orbit, then by this equivalence, we can say that the representation of G in the coordinate algebra of Z is not multiplicity free. Since Z is not spherical, this representation is not multiplicity free. There exists an irreducible representation of G occurring in this coordinate algebra at least twice. Now, since Z is a closed subvariety in X, we have a surjection of coordinate algebras from the coordinate algebra of X to the coordinate algebra of Z. This is a surjective algebra homomorphism. The kernel of this homomorphism is the vanishing ideal of Z, those polynomials which vanish on Z. Since Z is G-stable, this vanishing ideal is also G-stable. It is a G-stable subspace in this coordinate algebra. And by complete reducibility of representations of reductive groups, we can choose a complementary subspace, which is, of course, isomorphically projected onto this guy. So we have a decomposition of the coordinate algebra of X as the direct sum of this vanishing ideal and some complementary subspace, which is isomorphic to K of Z.
I have missed something.
What is vanishing ideal? So your question is, what is this guy? Yeah?
Yes, yes.
This vanishing ideal is the set of all polynomials on X which vanish identically on Z. So the defining ideal of your algebraic subvariety, of your closed algebraic affine subvariety. Okay.
So the G stable of this ideal is not relevant to the not multiplicity free condition.
No, this is not relevant to multiplicity free. This is G stable because this guy is G stable. The variety is preserved by the action of G, and this means that the ideal of this variety is also preserved by the action of G. Okay? This has nothing to do with multiplicity free. This isomorphism, this is an isomorphism not of algebras, but of G modules. So this coordinate algebra is isomorphic to this direct sum as a G module. As a G module. This isomorphism stems from complete reducibility of representations of reductive groups. So this is by complete reducibility.
The complete reducibility is valid for all G, right?
Yes, this is because G is reductive. A complete reducibility means that you always can choose.
Sorry.
Yeah, G is reductive. So you can always choose a G-stable complementary subspace. Okay. Now, since this guy were not multiplicity free, so this subspace were not multiplicity free, we see that this guy is also not multiplicity free, because it contains a K of Z as a direct summand. So let me write this explicitly. So we get that the representation of G in K of X is not multiplicity free. And this is a contradiction because X is assumed spherical. So we have proved this claim. We have proved that any closed irreducible G-stable subvariety in X contains an open B orbit, open in itself. Now we can finish the proof. So let me take maybe yet a couple of minutes to finish the proof. Okay? So the end of the proof goes by induction on the dimension of X. Well, first, since X is spherical, since X itself is spherical, it contains an open B orbit, and therefore it contains an open G orbit. Let me denote it by a Y naught. So this is an open G orbit. Open and dense because X is irreducible. The complement of this open G orbit is a union of irreducible components, Z1, etc., Zm, where these Zi's are closed irreducible G-stable subvarieties in X of smaller dimension. Since we prove now the theorem by induction, then by the induction assumption, we can say that each of these Zi's is spherical for G, for the action of G, because it has smaller dimension. And because, not because, I'm sorry, not because it has smaller dimension, but because of what we have proved on the previous page. Because we have proved that any closed irreducible G-stable subvariety is spherical. And now, since it has smaller dimension, then by the induction assumption, we can claim that G acts on each of these Zi's with finitely many orbits. And therefore, since G acts on each of these Zi's with finitely many orbits, and when you pass to X, you just add a single orbit Y naught, we get that G acts on X itself with finitely many orbits.
Professor, I have a question.
Mm-hmm.
So, why is the G-stable subvariety in the complement of Y naught is irreducible? I mean, G can.
No, I mean, not this whole complement is irreducible, but this complement is a closed subvariety in X, right?
Yes.
A complement to the open orbit is a closed subvariety, and we decompose it into irreducible components. These guys are irreducible components.
Component may not be G-stable, I think.
No, because G is connected. You cannot jump to another component by the action of a connected group.
Oh. G is connected. Oh,
yeah. G is a connected reductive group. So it does not permute the components, since it is connected. It preserves each component. Okay, so we have proved that the first statement of the theorem, that by induction of the dimension, we have proved that the action of G on X has finitely many orbits. And what remains to remark is the second statement, that each orbit is a spherical homogeneous space. But it is clear because if you take any orbit, so if you take any orbit Y in X, any G orbit, then its closure, denoted by Z, is a closed irreducible G-stable subvariety in X. But by what we have proved before, it is spherical. Well, maybe non-normal, but spherical. And therefore, the open orbit in it is also spherical. this proves the last statement of the theorem and the whole theorem, finally. So we have proved this finiteness result for...
Hey, so
yeah.
How is y different from y not?
Y is just another orbit, any orbit in X. Y naught is the open orbit, and Y is any orbit.
Oh, thanks.
Okay. So I have finished the lecture. So if you have still any questions, then please ask them.
So why there are only finitely many components in X minus Y0?
Well, because they are just irreducible components. These guys, these Zi's are just irreducible components of this complement. So this is a closed subset in X, and these are just its irreducible components. There are always finitely many irreducible components. Okay?
So they have the same dimension.
Excuse me?
I don't
say it
think
again.
So. They may not have the same dimension.
May not have same dimensions.
About the dimension. Now I understood the question. Yes, of course, they may have different dimension.
Okay.
They need not to have the same dimension. And this is inessential for the proof. What is essential is that the dimension is always smaller than the dimension of X, because we argue by induction of dimension.
Okay.
Okay?
Okay, thanks.
You're welcome. So, more questions? Comments? Whatever?
So the finiteness of the irreducible components comes from basic algebraic geometry, right?
Yes. This comes from our basic assumptions that we consider algebraic varieties in the classical sense, which are of finite type, Noetherian, whatever. So yes, this is just very basic algebraic geometry.
Professor, can I ask the last two lines here?
Yes.
So why? No, this page. Yeah. So
this page.
What does it? Yeah. What does it mean here for y subset must no? So G orbit here, and what do you prove here?
So we want to prove on these last two lines. We want to prove the second statement of the theorem, that each orbit on a spherical variety is a spherical homogeneous space.
Yes.
We prove this statement. So we take any G orbit in X. We have already proved that there are finitely many of them. And we now take any of these orbits and we close it up. What we get is a closed G-stable irreducible subvariety in X, right?
G-stable irreducible subvariety of X, yeah.
And we have proved here that such a subvariety is spherical. It contains an open B orbit.
Yes.
Okay. And if this Z is spherical, if Z contains an open B orbit, open in itself in Z, then of course the open G orbit in Z, which is Y, also contains this open B orbit. This means that Y itself is also spherical. So the picture is like this. So let me draw a picture. Maybe it may be it will be more clear.
I think you get it a little bit. I think there is a more easy way to say that Y is spherical, because the definition of spherical variety is that its open G orbit is already a spherical homogeneous space. So in the induction, we can assume that Y naught is a spherical homogeneous.
Well, I mean, this is a terminological discussion. When we defined what is a spherical variety, I said that you may define as an embedding of a spherical homogeneous space, which is the open G orbit. But also, I said that we can define what is a spherical variety without mentioning the open G orbit. We can just say that a G variety is spherical if it contains an open B orbit. This is equivalent.
I see. I remember this definition.
Yeah, so now we use this definition. So we have proved on the previous page that Z contains an open B orbit, which means that Z is spherical. And in particular, it contains an open G orbit, which is a spherical homogeneous space. So the picture, let me draw a picture. Since such a question arises, that let me just draw a picture. So you have this Y, you have this Z, which is bigger than Y. You close Y up, you add something on the boundary. This is Z. And also, since Z is spherical, it contains an open B orbit. Open B orbit. Since Y is an open G orbit, it has to contain this open B orbit. So these three sets are embedded one into another. This is the picture. Okay? Well, more questions? I have seen something in the chat. Well, this concerns maybe something in the middle of the lecture. Something about emptiness. Yeah.
Here we prove that it is a homogeneous. Homogeneous means it's a geometry, right?
Homogeneous means yes, it is a G orbit. So Gx transitively.
Okay, I get it.
Mm-hmm. So I'm not sure I understand the question in the chat. So it was a question from Mike about ampleness. So S is ample, S ample shows ample. Maybe Mike, you can address your question orally. If you still have it, just ask it using microphone. I'm not sure I understand it. Well, if you already got an answer, then of course this is fine.
Mike is using the private discussion and we cannot see the question.
It was a private discussion. It was, yeah, right. It was a private discussion with me. But let me repeat again that during the lecture, it is quite difficult for me to answer promptly questions in chat, either they are private or not. It is better to use the microphone. So, Mike, if you still have this question, then just say it loudly. Or you can write me on email, because so far I just don't understand the question. Okay. So, more questions, comments, whatever. Well, let me announce what will come on the next lecture. So this was the finiteness theorem, the first finiteness theorem, which I was going to prove that given any spherical variety, there are only finitely many orbits of the group G acting on it. What I'm going to prove next is a somewhat converse statement, that if you have a homogeneous space such that any open embedding of this space has finitely many orbits, then this homogeneous space has to be spherical. This theorem is more deep than the first one, and it will take me some time, maybe half of the next lecture, to prove it. And then, after proving this theorem, I will turn to the problem of classifying spherical varieties. I will introduce some invariants which will be used in the classification. Well,
so the next lecture will be on the inverse of this theorem, right?
In a sense, it is not, well, in a sense, it is an inverse theorem. Yeah, you will see the formulation. Actually, I just pronounced it, but I will write it precisely at the beginning of the next lecture. So yes, this will be the first part of the next lecture on Monday. Okay. So again, if there are no more questions or comments, then we may finish now. And again, let me repeat as usual that you are welcome to write to me on email, to ask questions, and also I ask you to try to solve exercises and to send me your solutions again on email. I will check and comment on them. So if there are no more questions or comments, then let me stop sharing.
Okay.
And yeah, anything?
Nothing.
Okay.
I'll stop the recording.
Yeah. So let me say goodbye